Hi there. In this video, we'll look at multiple choice problem 3 from the AP course description. In this problem, we're presented with a formula for a function, and we are asked to find which of the following statements is true. Okay, and this is a pretty text-heavy problem, so let me see if I can make it less texty. What they're really asking here is for us to count how many local extrema the function has and how many inflection points the function has. Okay, so let's go over the background knowledge that a person needs to have in order to determine the answers to these questions. Here we go. All right, so in particular, we've learned that to discover the local maxima of a function, we need to look and see where the slope of the graph changes from positive to negative. And to discover where the local minima of a function are, we need to learn where the slope changes from negative to positive. Okay, so in both of those cases, the first derivative will undergo a sign change, either from plus to minus or minus to plus. Okay, so in terms of our strategy here, if we want to count local extrema, we need a formula for the first derivative, and we'll look for sign change from plus to minus or minus to plus. Okay, let's discuss inflection points next. All right, so the idea here is that a point of inflection occurs where the bending changes. In this case, it's bending down up to the inflection point, and it's bending up away from the inflection point. And what we've learned in previous lessons is that the sign of the second derivative is negative at places where the graph bends down, and the second derivative is positive at places where the graph is bending up. Okay, so in this particular case, you would see a sign change from negative to positive for that second derivative, signaling a point of inflection. So the idea here is that at inflection point, the second derivative will change sign. And if I flip this graph around, you might have seen it go the other way from where it's. Let me just quickly draw what I'm thinking here. All right, so it might go from where it bends up to where it bends down. And in that case, you'd see a sign change in the second derivative from plus to minus versus minus to plus. All right, so one way or the other, to discover how many inflection points there are, we need to analyze the second derivative, and we'll see sign change in one direction or another. Okay, so with that, let's go ahead and start computing derivatives. And this is a pretty simple function, so the derivatives are going to come real easy. Original function is here. First derivative is going to be 4x cubed minus 6x squared. And let's now take another derivative. So the second derivative is 12x squared minus 12x. Okay, and once again, we're looking for sign changes for this guy and this guy. Okay, so in order to discover sign changes, we need to look at and see where these guys are 0. All right, so I've summarized those three formulas, the original function, the first derivative, and the second derivative. Those formulas are summarized here. And in order to find zeros, we would like to just factor things. Okay, so here I see a common factor of x to the third power. Can be factored out. And we're missing a factor of x and a factor of 2. And this formula will be 0 at exactly 2 places, when x is 0 or 2. So those are the zeros of f, just for completeness. All right, for f prime, we have a common factor x squared that we can factor out. And here we're missing a factor of 4x. Here we're missing a factor of 6. Okay, and so it looks like this formula will be 0 when x is 0, or 6/4, which is 3/2. So those are the zeros of f prime. All right, for f double prime, we have a common factor of 12x that we can factor out. And here we're missing a factor of x. Here we're missing a factor of 1. So the zeros of f double prime are 0 and 1. Okay, so let's just pop over here, or rather, let me shrink this down so that I can begin to understand what the function looks like. Okay, so I'm going to be making some number lines, and I'm just going to keep it easy and make 3 separate number lines. One for f prime, and one for f double prime. So let me label those for you for clarity. Okay, and now I'll single out the zeros of each of those 3 functions. So we'll put 0 down as an important number, and here's 2. Okay, and why don't I just go ahead and figure out what the functions does. All right, so we have x cubed times x minus 2, and we know that you're going to get 0 at these values. Okay, what happens if I plug in a number that's bigger than 2? Well, you're going to get positive answers. If you plug in a number between 0 and 2, you're going to get one of them positive and one negative, so the product is negative. And if you plug in some negative number, you get the product of 2 negatives, which is positive. So this is what I would expect to see in terms of the original function values. Okay, now let's turn our attention to the first derivative. Zeros are at 0 and 3/2. So here's 0 again, and 3/2. And if we look at the formula, we have x squared, which is either 0 or positive, so we can essentially ignore that. And if you plug in values, you'll see that substituting a number bigger than 3/2 gives positive answers. If you plug in a number less than 3/2, you'll get a negative answer, even if it's less than 0. All right, and now we're on to, let's see, the second derivative, which has zeros at 0 and 1. 0 and 1. Okay, so if we plug in a really big number, we'll get 2 positives. So that happens. If we plug in, let's say, a half, you're going to get 1 positive and 1 negative. And if we plug in a negative value, we'll get the product of 2 negative numbers, so the product should be positive. Okay, so let me see if I can paste my work over into the next page so that we can see if we've done everything correctly. And before I do that, let me actually see if I can predict the answer to this multiple choice question. So I'm just going to hide this for a moment, if I can do that. All right, we would expect to see, in terms of counting local extrema and inflection points, every time the first derivative changes sign, we would expect to see a local extremum. And there's really only one sign change from negative to positive right here around 3/2. So let's put 1, and let's be specific here. Negative to positive looks like that. 1 local min, no local max. So 1 relative extremum. That's our prediction. Okay, and now let's turn our attention to the second derivative so we can count inflection points. How many sign changes do we see? Positive to negative, negative to positive. 2 sign changes, 2 inflection points from concave up to down. I won't try to draw that right now, but 2 points of inflection. All right, so 1 local min, 2 points of inflection, and let's see if we can identify that answer. Let's see, 1, no, that's not it. Okay, I need 1 relative extremum. This has 2, so that's wrong. No relative extrema. No, that's not right. Let's see. 2 points of inflection, looking good. 1 relative extremum. Well, that matches my work, so this must be the right answer. Can I rule out the others just for certainty? This has the wrong number of these, and this has the wrong number of these as well. All right, so it looks like the answer is C. Can we just confirm and take a second to make sure that our answer is right and that everything makes sense? Okay, really kind of pulling some things together here. So what I'm going to do is try to paste this over onto the page. You know what I'll try here? Let me paste the graph onto this page. Maybe that's easier to do. Okay. And can I even line it up with my numbers? That would be so handy. There we go. Okay. Not perfect, but good enough. All right. So let's see if everything is making sense with the work that we've done so far. Okay. So according to our analysis of f itself, we should see positive values and then 0. And we do see that. Positive values and 0. Negative values, that's below the x-axis. Negative. And then 0. Yep. Positive. Yep. All right, so all this is showing we are seeing positive values up here, and then 0. Negative, negative, negative values in here, and then 0. And positive values over here. Okay, so our analysis of the function itself and its zeros makes sense from that standpoint. Whoops. Okay, next let's turn our attention to the first derivative, which is what this problem was really about. And we should see negative first derivative, so decreasing. All right, and the function is indeed decreasing. And then it's flat. Yep. Still negative. Still negative. And let's see what's supposed to happen there. We should see a flat point at 1.5. I think my scale is just a little off in my drawing. But we do see a flat point there. And then plus, so increasing. The derivative is positive, it's increasing. Okay. So what that's telling us is, if I can rewind, all right, the sign of the first derivative tells us that the function should decrease, and then still more decreasing, and then increase. And that's exactly what it does. All right, so our analysis was correct as far as the first derivative. Let's keep rolling with the second derivative. Positive second derivative says concave up. Switch to concave down, concave up again, and inflection points at these two numbers. All right, well, this is concave up, point of inflection, concave down, point of inflection, concave up. All right, so let me go back and label for you. So here are the points of inflection right here. And what did we say at 1? Okay, so it looks like we're bending up, bending down, bending up again. All right, so this was just to help you see that all of our work actually fits with the picture of the graph that Desmos has produced. And so that confirms that all of the calculus is working here. And so that is a good thing. Okay, lastly, it's just important to always be connecting this work back to the topic outline and see how does this problem fit with the course goals. So what came up in this problem? Well, number 1, local extrema, relative maximum, relative minimum. That came up. Number 2, points of inflection. Okay, and the idea of concavity tells us about the point of inflection, which was related to the sign of the second derivative. Okay, I hope that this video was helpful to you in terms of understanding these things, and we'll see you next time.